Welcome to Gokul Global University e-learning. Today's subject is electromagnetic field, and we are going to cover the sum of points in current presentation, that is Coulombs law, electric field intensity, electric field due to continuous charge distribution, electric flux density, Gauss law, and electric potential. In basic course of physics, you have already studied that between two point charges, either a force of attraction or repulsion exists depending upon the nature of charges. In the course, we calculated only magnitude of the force. It was not expressed as vector, but force is a vector quantity and acts along the line joining the 2 point charges. The law used to calculate the force is called Coulombs law. Between the 2 point charges, there is a force of attraction or repulsion depending upon the nature of charges. What we have seen here. If the charges are like charge, there is a force of repulsion, and in case of unlike charges, it is a force of attraction. The force is a vector quantity which has both magnitude and direction. The magnitude of force between two electrical charges is given by Coulombs law. Experiment conducted by Coulombs show that the following hold for two charges bodies that are very small in size compared to their separation, so that they can consider it as a point charges. So what is the statement of Coulombs law? It states the magnitude of force is proportional to the product of the magnitude of the charges, that is Q1 and Q2. Second, the magnitude of the force is inversely proportional to the square of the distance between the charges. Means it is inversely proportional to the square of the distance between the charges. If the distance between the two charges is let us say r, then it will be 1 upon r square. The magnitude of the force depends on the medium. So medium is given by epsilon, we will see it later. Thus, if we consider 2 point charges q1 coulomb and q2 coulomb separated by a distance r meter in a free space, the force is given mathematically as F is equal to k q1 q2 upon r square. The unit of force is in Newton. The constant of proportionality k is given by k is equal to 1 upon 4 pi epsilon. What is epsilon? Epsilon is equal to epsilon 0 epsilon r, that is the permittivity of media. Epsilon r, that is the relative permittivity. Epsilon 0 is equal to permittivity of free space, which is 8.854 into 10 raised to minus 12. For free space, epsilon r, that is 1, and epsilon is equal to epsilon 0. Thus, the magnitude of force is given by F is equal to Q1 Q2 upon 4 pi epsilon r square Newton. Or in general terms, we can consider as shown in figure, the force between 2 points F1 and 2 is given by F12 is equal to Q1 Q2. What is R? That is R2 minus R1 upon 4 pi epsilon 0 R2 minus R1 cube. If we have more than 2 point charges, F is equal to Q upon 4 pi epsilon 0, summation runs from K is equal to 1 to N into Qk R minus Rk upon mod R minus Rk cube. This is the formula for we have more than 2 point charges. Now let us have little looks on electric field intensity. Electric field intensity generally given by E bar. Now consider a positive electric charge Q1 is fixed in a position. If another positive point charge is brought into the vicinity of Q1, it is acted upon by a force. If this second charge is moved slowly around a charge q1, we note that there exists everywhere a force on this second charge. In other words, the second charge is displaying the existence of a force in a region surrounding the charge q1. The region where force acts is called as field. The definition of electric field intensity. In the system of two charges, if the second charge is a positive test charge q, let us say it is qt, which is sufficiently small so as not to disturb significantly the field of first charge q1, then the electric field intensity E bar due to q1 is defined as the force per unit charge on q2. That is, electric field E bar is equal to force on test charge given by F upon test charge, that is Q. So in general terms we can say E bar is equal to F bar up by Q. We can also write like E is equal to Q upon 4 pi epsilon 0 R square into unit vector AR. The unit will be Newton per Coulomb N upon C. As we can see, E is equal to F by Q. The unit for F is Newton and for Q the unit is Coulomb. So we can, in general terms, in vector forms, we can write like E is equal to Q into R2 minus R dash upon 4 pi epsilon 0 mod R2 minus R dash cube. If we have more than 2 point charges, we can write like A is equal to 1 upon 4 pi epsilon 0 summation runs from k is equal to 1 to n qk r minus rk upon r minus rk cube. Let us say electric field due to continuous charge distribution. If there is a continuous charge distribution, say along a line, on a surface or in a volume, you can see from the pictures that is a point charge, that is a line charge, a charge distributed evenly on a line, the charge distributed in a particular surface, that is surface charge, and the charge within the enclosed volume, that is a volume charge. The charge element dq and the total charge q due to these charges distribution can be obtained by the following formulas, that dq is equal to rho L dl up to q is equals integration from line dl is rho L dl, that is the line charge, dq is equal to ds rho s ds is equal to integration surface rho s ds, that is surface charge, dq is equal to rho v dv is equals integration from volume rho v dv, that is the volume charge. The electric field intensity due to each charge distribution rho L, rho S and rho V may be given by the summation of the field contributed by the numerous point charges making up the charge distribution. So E is equal to integration rho L dl upon 4 pi epsilon 0 r square into unit vector AR, that is the line charge. E is equal to rho some integration rho s ds upon 4 pi epsilon 0 r square into AR, that is surface charge, and E is equal to integration rho v dv upon 4 pi epsilon 0 r square into AR, that is a volume charge. Now we'll see little looks upon electric flux density, Gauss law and divergence. So before starting, the electric field about a point charge, we have studied that E bar is equal to Q upon 4 pi epsilon r square into unit vector AR. The equation shows that at any point the electric field strength E bar depends not only upon the magnitude and position of the charge Q, but also upon the dielectric constant of the medium, that is, that may air, oil and others, in which the field is measured. It is desired to associate with the charge Q at a second electrical quantity that will be independent of medium involved. The second quantity is called electric displacement or electric flux, and it's generally given by a psi. So we must consider what is Faraday's experiment. To understand what is psi, Faraday made the experiment with the concentrating sphere will help us. A sphere with charge q was placed within but not touching a larger hollow sphere. If there is any charge initially present on the outer sphere in order to remove it, the outer sphere was earthed momentarily and then the inner sphere was removed. The charge remaining on the outer sphere was then measured. This charge was found to be equal and opposite to the charge on their inner space. The electric displacement is denoted by the psi. The electric displacement psi is equal to QC. The electric displacement also called as displacement flux or simply electric flux. As you seen that electric field intensity depends on the medium in which the charge are placed. Suppose a vector field D independent of the medium is defined by D is equal to epsilon 0 into E. The electric field psi in terms of D can be defined as psi is equal to integration D dot ds. The vector field D is called the electric flux density and is measured in coulombs per square meter. For an infinite sheet, the electric flux density is given by D is equal to rho s by 2 into An. For a volume charge distribution, the electric flux density D is given by D is equal to integration rho v dv upon 4 pi r square into Ar. In both the above equation, D is function of charge and position only. We could have obtained the result for this special case more simply by multiplying q upon 4 pi r square by the area of sphere 4 pi r square. Let us state that the total electric flux psi through any closed surface is equal to the total charge enclosed by that surface. That is simply psi is equal to q e n c means q charge enclosed. Psi is equal to integration d psi equals circular surface d dot ds. You can say is equal to total charge enclosed q is equal to rho v dv. So the total q is equal to integrations d dot ds is equal to integration v rho v dv. Let us say equation 1. Using divergence theorem, we can obtain circular integration d dot ds is equal to integration v del dot d dv. Comparing two volume integral in equation 1 and 2, we can have rho v is equal to del d. This is the first Maxwell's equation. State that the volume charge density is the same as the divergence of the electric flux density. Keep in mind, it states that the volume charge density is same as the divergence of the electric field density. What are the applications of Gauss law? Gauss law is used to find D or E due to some symmetrical charge distribution like point charge, line charge, surface charge, volume charge, coaxial cable, and so on. The application of Gauss law. In electrical engineering, the potential is generally denoted by V. The source of potential may be point charge or other types of charge configuration. Initially, we shall obtain expression for the potential due to the point charge, and then this idea can be extended to obtain V due to other types of charge configuration. So what is the potential P? P is nothing but the work done upon charge. Electric field intensity E. Due to a charge distribution can be obtained from Coulombs law or using Gauss law. When the charge distribution is symmetric, we can obtain E without involving vectors by using the electric scalar potential V. From Coulombs law, the force on the position charge Q is F bar is equal to Q into E bar. The work done in displacing the charges by length dl is dv is equal to f dot dl, that is equal to minus q into e bar dot dl. The negative sign indicates that the n or being done by an external agent. The total work done or the potential energy required in moving the point charges q from A to B is given by the work W is equal to minus q integration from A to B E bar dot dl. Dividing the above equation by q gives the potential energy per unit charge, that is work done by charge, that is q upon W upon q is equal to minus integration from A to B E bar dot dl. This is nothing but VAB, means the potential between the point A and B. The VAB is known as the potential difference between points A and B. To conclusion, if VAB is negative, there is loss in potential energy in moving Q from A to B. Work is being done by the field. If this is positive, there is a gain in potential energy in movement. An external agent does the work. It is dependent on the path taken. It is measured in joules per coulomb, referred as volt. The potential at a point due to a point charge q located at the origin is given by V is equal to q upon 4 pi epsilon 0 r. The potential at any point is the potential difference between that point and a chosen point at which the potential is 0. Assuming 0 potential at infinity, the potential at a distance r from the point charge is work done per unit charge by an external agent in transferring a test charge from infinity to that point. If the point charge q is not at origin but at a point whose position vector is r dash bar, the potential Vr dash at r dash becomes Vr dash is equals q upon 4 pi epsilon 0 mod r dash r bar minus r dash bar. For n point charges q1, q2, q3 up to qn located at point with the position vectors r1, r2, r3 up to rn, potential at r bar is given by Vr bar is equal to 1 upon 4 pi epsilon 0 summation from k is equal to 1 to n qk upon mod r bar minus rk bar. If there is a continuous charge distribution instead of a point charge, then the point potential at r dash becomes Vr is equal to 1 upon 4 pi epsilon 0 integrations from L rho L r dash dl dash upon r minus r dash, that is for line charge. For surface charge, V bracket r is equal to 1 upon 4 pi epsilon 0 integration s rho s r dash ds dash upon r minus r dash, that is for surface charge. For volume charge, Vr is equal to 1 upon 4 pi epsilon 0 integration from V rho V r dash dv dash upon r minus r dash, that is for volume charge. I hope guys you can understand all this point we have discussed, and if you found any doubts you can comment in comment box. In next presentation we will see relation between E and V. The polarization in dielectrics, field due to the polarized dielectric constant and the strength, continuity equation and relaxation time, etc. In our next presentation we will see that. Thank you guys. We will meet in next lecture.